This will be our last section before the second test of the year. So again, we're doing 3-1 to 3-4 today. And then on Tuesday, we're going to be testing the projects for about 30 minutes. And then I have an activity for the second 30 minutes that'll help for review for the test on Thursday. Okay? Your second test is obviously Thursday. If for some reason you're out on Thursday, you got to make it up on Friday. Grades are due Monday morning for the second quarter. So make sure you set it up for me that you come in on Friday. Or if you know for some reason you're going to be away, say Thursday and Friday, you need to take the test Wednesday, or you're going to get an incomplete for your quarter grade. Okay, you don't want to get an incomplete because then it just gives a headache for you, for me, and then for Miss Holden as well. Okay, so please make sure that you are here, obviously. So vectors from last lesson. A vector has two things. What are they? A vector has two things. They are? Direction and magnitude. Very good. So when I take a look at this next slide, I can see exactly that. The magnitude is the length of the vector. So when I say the velocity is 3 meters per second east, the magnitude is 3 meters per second. A velocity of 3 meters per second east, its magnitude is 3 meters per second. Its direction is east. Or you could say along the positive x-axis. Right? Think about east. East is positive x-axis. If you don't know this, write it down. West is positive east, is the negative x-axis. North is the positive y-axis, and south is the negative y-axis. So just like you would draw your x-y axis, you draw north, south, east, west. Okay, so on a quiz, on a test, on the problem sets, this is your general schema right here. But recognize if the problem says along the negative x-axis, it means west. It means exactly west. Now, we also give directionals with respect to the axis. So let's discuss what this means. So if I had a vector that was 2 meters at 45 degrees northeast. 45 degrees northeast. Who remembers what I mentioned? I mentioned it real quick last class. What word do you put between north and east? Christina? Of. Put the word there. Trust me on this. It will make you remember so much easier. North of east. What does that mean? Okay, ready? I go over to east, that's east. And then what's north of that? It would mean I take my arm and do this, right? So that tells me where the angle is. So the angle is right here. So when I'm drawing this vector right now, I'm going to draw the vector and I'm going to move and I'm going to go east. And let's make this actually 30 degrees, not 45. Make this 30 degrees. Because 45 is right in the middle and then you're not going to know which one I'm referring to. So 30 degrees north of east. I go over to east like this, and then I go about 30 degrees up, and I connect my vector from the origin to that dot that I'm showing you right there. Okay, so again, that's my vector. This is my angle theta, 30 degrees, and this is my magnitude, 2 meters. So this vector literally is a 2 meter length at an angle of 30 degrees north of east. 2 meter length at an angle of 30 degrees north of east. What about southwest? What would that look like? Southwest. George.
Will it be south of west? So you go to west and then you go south of that?
Yeah, and then you go south of that. Very good. So the 30 degrees on that side is going to actually look like it continues the line, right? Because 30 degrees south of west would look like this. Okay, that would be if we had the second option again, 2 meters at 30 degrees southwest. So this looks like a continuous line, and it is actually because the angles are the same on both sides. What kind of angles do we call these? Geometry? Quick vocab recap? Geometry? Vertical angles, very good. 30 and 30 are vertical angles. Hey, geometry comes up a lot in physics, okay? A lot in physics. You'll notice that, especially in this section. We do a lot of triangles. Okay, a lot of parallel lines and perpendicular lines. So let's jump to the next slide here. So how do we visually add vectors? So you did this already, luckily. It was that method that Emily talked about. The method is actually called tip to tail. That's what the method is called. But you don't have to know the name of it. It's not going to come up ever. But you need to know how to use it. So what do? You connect the tip of the first vector to the tail of the second. So we literally take the first vector and draw it by itself. And there's the first vector. Okay, literally redrawing the first vector. I know it's maybe not exactly the same length. I'm trying. Then I take the second vector and continue that from where the first one left off. Okay, there's the second vector. And you can see, obviously, on the right, you can see it already. I'm trying to show you. And then the third vector. Where did we start? Well, we started at the beginning of the red vector. Where did we end? At the end of the green vector. So my displacement, or what we're going to call resultant, VR, vector, resultant. I use just capital R, you can see. But my resultant is from the beginning of the red line, I'm going to write it or draw it in yellow here, to the end of the green line. That is my resultant vector. So what does this mean? It's very much like distance and displacement. Luckily for you guys, in the first chapter, I've already discussed this idea. So this should not be new, the idea of displacement and distance. When I walk like this, and then I make a turn, and I come all the way around, and I come back around to here, I can say that I started in the front middle of the room, and I ended here. So my displacement is the direct line from where I started to where I ended, the yellow vector. My distance traveled is the sum of the three vectors I just took, of the red, black, and green vectors. So what was that statement that we wrote earlier on about the relationship between distance and displacement? We used the inequality symbol for this. We used an inequality symbol for distance and displacement. Mara, go ahead. Very good. That was the statement we made. So what we can do is this. We can make this statement. I could say the overall displacement length, VR, has to be less than or equal to the sum of each of the vectors' distances combined. Notice what's not on top of each of those V's. What did I drop off when I wrote this statement here? What did I drop off, George? Yeah, it's not a bar actually. It's an arrow. Sorry, that's okay. They're arrows. They're little arrows. Just you can't see them. The arrow indicates that it's a vector, but when I don't include the arrow and I'm referencing said vectors, it means that I'm talking about the length of the vector. Write that down, please. So when you're discussing or when you're naming a vector, the value without the arrow above it indicates that you're talking about the length of that vector or the magnitude. The length or the magnitude of that vector. So again, the resultant, which is in yellow, is less than or equal to the sum of the other three. Now, when would it be equal? When would it be equal? It's never going to be greater than, because obviously less than or equal to means it cannot be greater. When will it be equal?
When you travel in a straight line, the distance is the same as your displacement.
Yes, very good. When you don't make any turns. Very good. No turning allowed. Write that down. Okay, again, your resulting vector will equal the sum of your independent vectors if you don't make any turns. And I mean, you can't turn right, you can't turn left, you can't turn around and come back. You cannot make any turns. If you make turns, it will not be true.
So I understand that rule, but if you go forwards, then backwards more, and then forwards again,
your distance is still greater.
It's still great, yeah.
The distance is 5 meters, another 5 meters, another 5 meters. My distance is 15. My displacement is only 5.
Right.
Make sense?
So the distance would be 10, it would be 15.
The distance would be 15. 5, 5, 5, whereas the displacement would just be the net 5 you traveled
Oh,
forward.
okay, so when you go back 5, it's not negative 5.
For displacement it is, but not for distance.
Okay.
Okay? Displacement is a vector, so that matters the direction. Distance, remember, is a scalar. It doesn't matter the direction. Scalar, the word scalar, if you want to jot it down, is just not a vector. Scalar is only what? It doesn't have a direction, it only has a, is that the word? Magnitude. 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 Okay? A scalar only has a magnitude. A scalar only has a magnitude. All right, let's take a look at this first example. Based on what you did yesterday with Google Maps, this should be cake. Okay, this should be real easy for you to do. So work through with the person next to you. I would recommend starting down at the bottom left here. Okay? And try to figure out why I said start at the bottom left. Use your context of the problem to think about that. Spend about 4 minutes on this problem. It shouldn't take you more than that. Draw your vectors first, please. Please call me over if you need help. If the Google Map lesson was a little bit confusing, I'm happy to come by and show you what I'm talking about here. Great trick.
Oh, okay, and then we have to somehow find out what this one is.
So this is how.
Yeah.
There's no like exit points for each one, because both sides have to
3, 4, 5.
North is positive y, east is positive x, stuff like that.
Okay, so now we just find it by like.
You can draw it kind of like this, okay? You know that? I think it's good
Okay, so basically, like this is 3, and this is 8.
Yep. I apologize. Maybe start a little bit higher up if you notice. Start a little bit higher up. I realized I started a little bit too low.
Yeah, you're right. Yeah, I said that's not fine.
I mean, the next one.
Take a look at mine, please. Make sure yours looks similar. Not the answer, just the diagram for now. Make sure yours looks similar.
I got 8. Oh wait, I'm sorry, I was doing it by like actual units. Oh, okay, yeah.
So the distance is.
Check your work here. Check your work for the length of the lines. Check my work too, obviously, but I think it was 3 down, 8 over, right? Well, it depends on the context of the problem. So if you're going to have to use that number later, you probably want to leave it as an exact value of bracket 74. But if you give me an answer as a final answer, which you're going to, you probably put it to the nearest 10.
Yes,
Obviously,
that's
this is
So she's translating on that 0.85
Oh, thank you. Sorry, they're all decimals. Sorry. I'm using miles instead of point. Yeah. These are all decimals. So does it make it 0.73? Is that what it comes out to, right? Yeah. Okay, that's all right. Francisco, yeah? Thank you. Yeah, they're all decimals. Sorry. All right, so let's stop and ask. Let's ask and look at the angle here. Look at the angle here. So, how do you know what angle theta is? Go to your starting point. Okay, go right here to your starting point. Then go to your ending point right here. Now, from your starting point, this is a very easy and a good technique to use, and it'll help you every time to figure out your angle. From your starting point, here's what I want you to do. Draw what you consider an x-axis or a horizontal line through your starting point. If you do that, every time you will not have a problem. So go ahead and just draw a random axis through the starting point. Once you do that, the angle between the vector and the horizontal axis you just drew will always be theta. So theta in this problem is this angle right here. Okay, so again, in my diagram on the right, this is theta. Is that clear what I'm saying? This angle right here, the resultant vector in green, the horizontal axis I drew through my starting point, sweep that out, and that's theta right there. So when I want theta in this diagram, what is it really in my triangle? In my triangle, where is theta really? Where is it in my triangle? Come on. I'm seeing it, right? Come on, I'm seeing it as well. Okay.
Down into the right of the middle.
Very good.
Like
Right
you
here.
said, across, yeah.
Yep, the bottom right. Because what are those? What kind of angles are these?
They're internal.
Yeah. Alternate interior. Good, in turn. I know what you meant. Alternate interior angles. Alternate interior angles. Okay, cut by a transversal. The transversal is the hypotenuse. So the theta value that you're looking for, okay, although it's shown there, it's really this theta right here. They're the same thing. But when you give an answer, what directional is it going to have? What's the directional on the answer going to be? Southeast. Very good. My theta is here, so watch. Ready? I'm here. I would normally think, okay, go east, but I'm going to go south of east. South of east. This would be east, but I'm going south of that. So I know already that my number is going to be at some angle southeast. I got to fill in that blank and then fill in that blank. So what's the square root of 0.73 approximately? Give me like, I don't know, 2 decimal spots. Caroline, go ahead.
It's 0.85.
What is it?
Well, it's 0.85.
Thank you. And that's going to be miles. And then what's my angle going to be? How do I figure out my angle? Even from last class, you guys came up with I think some of you came up with a pattern. You picked up on the pattern. Whenever you want to get theta, what can you always use? What function are you always going to end up using? It just happens to work out this way. What do you think, Christina? Yeah, the tangent inverse. Because look, if I'm looking for this angle here, it's always going to be opposite over adjacent, which is tangent. So my statement is going to be that the tangent of theta equals the y value over the x value. Right? The y value is 0.3. The x value is 0.8. So to get theta, do the tangent inverse of that value. Now, in your math course this year, you are going to be using what's called radians a lot. Radians are something you're going to use in math. Have you talked about that yet? Okay. So later in the year, you may use your calculator and turn the mode to what's called radian mode. For now, we're going to have the mode on degree mode. So if you're not sure if yours is or isn't, go ahead and press second tan and type this in and see what you get. If you don't get the same answer as everyone else, you got to go to your mode and change it from radian to degree. What do we get for theta in this problem? What do we get for theta? Jack, ahead.
20 and a half.
20 and a half. And we're in degrees. That is my full vector. And why do I say full vector? Because what was 0.85? 0.85 is simply the magnitude. And then 20.5 degrees southeast is the direction. Okay, that's where this came from right here. Anybody disagree with that, by the way? I didn't check it in. I took Jack's word. I'm assuming he's right for this. Yeah? Can you nod someone?
Well, I got like 20.56, so if we put 20.6, would that still be okay?
Yeah, depending on what you round it to here. So I happen to round, actually these. Is it 0.56? So 0.6, yeah, 20.6. It's fine. Yeah, but be careful when you're rounding there, okay? All right, let's move on to the next thing. Is that clear? Okay. Vector addition is commutative. Or on the next slide. Vector addition is commutative. And what does commutative mean in math? What can you do? What can you do? So let's take a look at 2 things. 2 ideas. First, vector.
Can you go back for 1 second? I'm just writing down the answer.
Math when you hear commutative, yeah.
Rearrange things.
Rearrange things. So 5 plus 3 equals 3 plus 5. That is absolutely true. Vectors follow the same rule. So look at the first diagram up here. When you do A plus B, start with A, then follow B, and your resultant vector is in purple. Anybody colorblind? Colorblind? Okay. Your resultant is in purple. Here, you start with vector B, and then add vector A. Your resultant is still this purple vector. Look at them. Look at this vector and look at this vector. They're identical. So A plus B equals B plus A. Okay, vector-wise. The second one, to subtract vectors. What is the definition of subtraction? Freshman year. Laura. Yeah, adding the opposite of addition. You physically add the negative of the second one. So vector subtraction is adding the opposite. So instead of doing a minus b, do a plus negative b. How do you represent the negative of a vector? If I'm moving at 5 meters per second, and then I say I'm moving at negative 5 meters per second, what do? What do? Flip it around. So what do I do with the vector? Flip it around. So instead of vector b, take a look at it real quick. Vector b starts up here and goes in the southeast direction. So instead of going up like this with A and continuing down with B, which is what I would normally do with addition, I'd go up and I'd continue down like that. Instead of going down and to the right, I go up and to the left with vector B because it's the opposite of it. So this is vector A plus negative vector B, and this is the resultant A minus B. So when you see subtraction, take the second vector and flip its direction. Flip its direction. Okay, this is the part we really want to get to today, is vector components, horizontal and vertical. And luckily enough for you guys, because you were very diligent students, you already did this in your summer packet. Whether you realize it or not, you did it already, with all the trig work that you did. So let's quickly talk about this. Write out my trig ratios. So sine of theta, cosine of theta, tangent of theta. The sine of theta equals opposite over hypotenuse. Well, from theta's perspective, the opposite is the vertical component. The hypotenuse is simply vector A. So the sine of theta is always going to be vector A. Opposite vertical component over vector A. The cosine of theta is going to be the adjacent or the horizontal component over vector A. And then the tangent of theta is always going to be the vertical over the horizontal. This is where that angle came from in the last problem. Remember we said the tangent inverse? The last problem we did, that example, the answer for theta was the tangent inverse of 0.3 over 0.8. The 0.3 was the vertical component. The 0.8 was the horizontal component. So the tangent of theta is always going to be y over x, vertical over horizontal. Now, what's really important is this. What's really important is that we take this one, take this one up here, and take this one down here, and we solve those for vertical and horizontal. So if I solve the first equation at the top for the words vertical component, I get God bless you. I get something's in the air. Everyone is sneezing, not just me. I get vector A times the sine of theta equals the vertical component. Again, think of vertical component as a variable. How would you get rid of vector A? You would multiply on the other side. Then the other part becomes vector A times the cosine of theta, and that equals the horizontal component. So these two things are going to be really like our governing ideas when it comes to vectors. Okay, those two statements. When you want to know the horizontal component of a vector, when you want to know how far it moves to the right, simply take the length of the hypotenuse, the vector itself, and multiply by the cosine of theta. Now theta will always be the angle between, write this down, theta will be the angle between the vector and the horizontal axis. The same exact denotion as the last example that we did. Again, theta is always between the vector and the horizontal axis. This is theta. If you use this as theta right here, see where I'm pointing? Use this as theta, your answers actually switch. And you'll talk about that more in pre-calc. I don't want to spend much time on that right now. But if you accidentally use this as theta, your horizontal and your vertical will be switched up. So if you're doing this in class and you get the opposite answer as your classmate for horizontal and vertical, it means you probably use the wrong angle theta here, or you switch cosine and sine. That's the other possibility. Okay, keep that in mind. So these two things that are boxed in, really important. And I think, if I'm correct, that they're already on your formula sheet, actually. I think they're on there somewhere. And somebody could verify that for me, it'd be nice. Anyone have the formula sheet saved in Notability? Could be quick access? I'd recommend doing that. Put it in Notability at some point. Valentina, thank you. I see you going for it. I think it's on the second page, maybe on the bottom. Oh, there it is. The first page on the bottom right. Okay, you see right triangle stuff. So it's the first page on the bottom right is where you're going to see right triangle. Okay, that's where you're showing the vector parts. Let's take a look at this exactly now, though. So, recall from yesterday, remember this diagram? Remember this? A lot of you did what for this diagram? You just sketched, right? You measured the boxes, you counted them, and that worked, and that was fine. Now, ignore, by the way, these numbers are different than the numbers you counted. I think what did you get yesterday here? 21 and 19? Is that correct? 21 and 19, I think? So, these numbers are different for a reason. So they're not using the boxes anymore, so make believe the grid lines aren't there. So in the problem, we're told that vector A was defined as a length of 12 and an angle of 20. So this is vector A, its length is 12, and take a look, the angle here is 20. Then vector B is a length of 25, which is this full length here, and this angle here is 60 degrees. This angle here is 60 degrees. Again, it is not the angle, somehow, how students do this, but some students try to measure the angle from here all the way down to like this axis. You're starting a new vector, so start a new horizontal here, and then measure the angle like that. So if it were me, I'd be labeling this right now as 60 and labeling this as 20, so I know later on what I'm referring to. Where do these numbers come from? See these numbers? 11.3, 4.1, that's the base, that's the height. 12.5, 21.7, the base, the height. How do I get them based on the last slide? Where do they come from? What are they physically? What are they? Jack, give me something.
Well, you just use the trigonometry like from before to get them.
Precisely, Jack. Very good. So really, this right here is the horizontal component of A. So we call it AX, horizontal, X. This is the horizontal component of B. So we call it BX. And how do we get AX? To get AX, we take vector A, which is 12, and we multiply it by the cosine of the angle. And to get BX, we take its vector, which is 25, times the cosine of its angle, which is 60 degrees. That's where those numbers are coming from. So we're using what we came up with on the previous slide to give us a value for the components in the x direction for A and B. How does it differ? Differ for the y direction. How does it differ for the y direction? There's only one difference in the y direction based on the previous slide. Juliet. It's sine. Very good, Juliet. Instead of cosine, you use sine now. So this length right here, the by value, is really 25 times the sine of 60. It's going to be tough for me to draw it here. This y value for A is really 12 times the sine of 20. Now, how do I get the overall distance in the x and the y direction, just like what you did yesterday? But yesterday, you physically counted the boxes across. Counting these boxes, then counting these, and adding them together is called segment addition postulate. Think back to geometry, I know. Right? You're like, oh, why did I learn these things? This is why you learn these things. Because you apply them in some form of an application-based science, which is what physics is. So your x direction is really the x component of A plus the x component of B, which is 11.3 plus 4.1, giving me 23.8. So I'm literally adding segment A plus segment B with segment addition postulate to give me 23.8. And the same goes for the vertical direction. 4.1 plus 21.7, right? 4.1 plus 21.7, giving us 25.8 along the vertical. So what would vector R be as a result? How would I figure out vector R as a result? What would I do? Caroline? Pythagorean theorem. 23.8 squared plus 25.8 squared equals R squared. We can come up with what R is. Then how do I get the angle? I say the tangent of theta equals the y value, the overall y value over the overall x value. So the theta itself is the tangent inverse of the overall y, which is 25.8, over the overall x, which is 23.8. And that will give me the theta value. Okay, I'm going to leave that for you guys to figure out on your own. This is just putting the calculator and figure out the value. Okay, so I have those two answers. How do I write my final answer? It's going to be R. Final answer will be R equals, first, whatever the R value is here, at whatever the angle is there, and then what's my directional for this problem? What is my directional? Just more? Come on, directional should be easy by now. Should see a lot more hands. Vin, go ahead. Northeast. Thanks, Vin. I'm only calling on people a lot, the same people, because the sake of time here. Let's see others' hands. Here's east. This is north of east. So the overall vector R goes east and then it goes north. So again, we say north of east. This number here comes from my angle theta. This number here comes from my length R. Seth, question? Sure?
Yeah.
Okay. Feel free to ask. I thought you did. Let's look at the last example for today. So you don't have to. Oops. Okay, let's look at the last example. So Mike starts at the southwest corner of Central Park and walks at an angle of 30 degrees northeast for 0.8 kilometers and then stops. He eats lunch and enjoys the wonderful weather before heading 25 degrees southeast for a half a kilometer from that point. Determine his overall displacement. What do you do to start these problems? What would really be useful? Drawing your axis or diagram. I agree. So I start by saying, okay, here's the origin. I'm going to go 30 northeast. So this is east right here. So 30 degrees north of east would be something like that. So there's my first vector. And if you want to, you could draw your horizontals as dotted. Hold on. There we go. You don't have to, but some students like to draw the horizontal as dotted lines. Why is this not erasing? Come on. There we go. Okay, so if you want to draw this dotted, you can. Then from where he stops and eats lunch and enjoys the weather, he then goes 25 degrees south of east. So again, draw east from where you stopped, and then draw south of east. 25 degrees, and this length is 0.5 kilometers. Therefore, his overall displacement is from A to B. So how do I find that overall length? Well, I have to start to think about my components again. So I'm going to use green to draw. Follow what I'm drawing in green. He first really walks up technically. I know he doesn't, but technically he does. And then he walks over. So make your triangle in green there. Then I'm going to use blue for my next triangle. He then walks east and south. I know he doesn't physically do it, but this is how I picture it. Is that clear? Again, Mike does not actually walk along the dotted green or dotted blue lines. But picture it that way so you can visualize your components. So take a look here. This is north, right? Hold on. This is north. This is south. So this vector component is positive because you're going up. This one is going to be negative because you're going down. This is positive because you're going east. This is still positive because you're going east. Okay, try to finish this one up over the weekend, please. Your homework is on the slide.